probably know me at this point. My name is Jack. I'm subbing in for Kevin. This is the third lecture. And in this lecture, we'll be covering some topics about polarity, Kevin covered sheet metal forming and shearing last week, so we will not be going over that. Joint types, weld types, and we'll also be going over welding callouts. It's all super important stuff. Take good notes. I know I went over a little bit of the basics of polarity in class, but I'm going to hit it again real quick as it pertains to the AC current and the modified wave shape. If you didn't take notes in class, now is your chance. So, so this is just a little bit more in depth of what we did in class, but when you weld aluminum, due to the oxide layer, which is that, this is aluminum, this is Al2O3, which melts at 3700 F, and you got your welding torch. Which is normally set up in DC electronegative for TIG welding. And as you can see by that little diagram on the screen, or at least I hope you can see it, it goes over the differences between direct current and alternating current and electropositive versus electronegative. In electropositive, you've got shallow penetration. You don't have you won't be able to make a very strong weld using DC electropositive on the TIG torch. However, the property that it does have is it will clean this oxide layer, which stops you from welding aluminum. So it's the cleaning cycle, and the electron flow is what causes it to be a cleaning cycle. As they leave the material, they break through the surface and they clean the oxide layer. This is all kind of stuff we went over in lab. Things we didn't cover in lab is that the negative terminal is the cathode in welding. So it all depends on where electrons are emitted or where they are received. And so the cathode is where they're emitted. So in DC electronegative, your torch is the cathode and your workpiece is the anode. In electropositive, it's the opposite, obviously. And the anode is where 70% of the heat is generated. So in DC electropositive, 70% of the heat is in the gun, 30% on the workpiece, which is where the shallow penetration comes from. And so what we have to do to be able to weld aluminum, to strip the oxide layer and to get good penetration and have it be a strong weld, is we have to use alternating current, which I went over. So you switch to this, a sine wave, where you have DC electrode positive, then you got DC electrode negative, but you have a problem where it only welds for 120 amps at the peak, if that's what you want to weld at. And so to make the equipment a little lighter and last a little longer, not affect the duty cycle as much, what you do is you make it into a square wave. This is all important stuff. It'll be on the midterm. So that keeps it pinned at 120 the entire time. But in this setup, you have 50% of the heat in both the workpiece and the torch. The get a more favorable welding cycle, they changed it to the modified sine wave. Modified square wave, sorry. Where 25 to 35% of the cycle is DC electropositive cleaning. Yeah? Let's all just review from what I told you in lecture, or in lab. So, something new, I don't know if Kevin covered this, but consumables. We have not done this in lab yet. However, it's exactly the opposite as TIG welding. So the difference between TIG welding and, let's say, stick or wire feed is that the electrode is not consumed in TIG welding. And that's like the overarching difference between the two. So DC electropositive is where the penetration comes from in in stick welding and wire feed. Does that make sense? Does that confuse anybody? And the reason for that is a little bit hard to understand, but basically what happens when the electrode is being consumed is that as the electrons collide with the filler rod, the thing that is being consumed in the process, they heat it up and melt it into a ball. That ball, once it gets to a certain weight, is then pulled across the arc gap into the weld pool, and it maintains 90% of its heat, which I think is in the next slide, but I'll stay here for a second. And that heat is then lands on the plate, which has 30% of the heat from the electrons leaving it. Which then means that you're going to have good penetration because you've got 90% of the 70% landing on the plate, and so then you have most of the heat just winding up on the plate and not on the electrode itself. Whereas when you weld in DC electronegative using a consumable process, what happens is the workpiece does heat up, and it heats up with 70% of the heat. However, when that ball falls from the electrode, it falls cold. It's not hot. And so when it lands in the weld pool, it sucks heat out of the weld pool, and it causes poor penetration because it essentially is preventing the material from going deep within the workpiece. So yeah, this is where I talk about DC electropositive. 90% of the heat is retained during the transfer. So that means most of the heat is in the workpiece. When you are doing SMAW, which is shielded metal arc welding, especially when it pertains to stick welding, there is something called a pinch effect, which is as you are welding with direct current, the flow of electrons basically create a magnet while you were welding. And so as that ball is forming on the end of the electrode, there's a magnetic force that causes the end of the electrode to begin to pinch and neck off until the ball is pulled across the arc gap with the magnetic force, not just gravity, into the weld pool itself. And that allows for all kinds of different positions when doing stick welding, is what makes stick welding so versatile. You can weld directly overhead, you can do vertical welding, which are not true for TIG welding. TIG welding is very limited in terms of the position you can do it in because it is highly affected by gravity. So as you are welding, if you're welding above your head trying to do TIG, as you melt that weld pool, it'll want to drip away from where you're welding because gravity is not holding it in place and you don't have a magnetic force pulling the material into the weld. And that also can be true in wire feed. However, that gets into the modes of transfer, which will be covered in later lectures. Just so you know, there are 3 different modes of transfer, or I guess technically 5, but 3 main modes of transfer that are used in wire feed, which are globular, short circuit transfer, and spray. And some of those can be done in all positions as well, due to the pinch effect. You guys good? So, joint types. This is where I believe we're going to be getting into some new material. This is essentially just how you join 2 separate pieces of material. There are 5 basic joint types, and pretty much every kind of welding will fall under one of these categories. Even if it's not a flat plate, if it's like a round tube, it'll generally fall into one of these 5, regardless of the shape of what you're welding. And the 5 basic joint types, from easiest to hardest in terms of how it is to weld, are an edge joint, a T-joint, butt joint, center joint, or sorry, corner joint, not center joint. And I guess lap joint was the first one that I missed. But essentially what can make these easy or difficult to weld is the amount of heat sinking or backing you can have on the actual workpiece itself. So as you'll notice on the T and lap joint, you are welding in the center of a piece of material, or at least not on the edge. And that's what gives you some like beneficial effects in terms of welding it, is that the plate itself can act as a heat sink, because when you are not on an edge, the heat can disperse in every direction on the plate, which will pull heat away from the weld pool, making it a less precise process. You don't have to control your temperature as well. The butt joint, which is what we've been doing in lab a ton, is actually a harder weld than, say, a lap joint, because you are welding on both edges of the material. And that's why you've seen when you put too much heat into the plate, the edges pull apart, and it is difficult to weld when that happens. And that is simply because the heat doesn't have anywhere to go on one side or the other of the edge, and it's just concentrated there. And it's exaggerated when you get to the either side of the workpiece. When you're in the center of a butt joint, it's easiest because the heat can disperse outwards into the plate. But when you're on the edges, it can't go one direction, and so you're more likely to burn through on the edges, and that's why I have told you to roll off the pedal as we come to the edge. A corner joint is the hardest, and that is because you're not only on both edges, but it is extremely hard to get backing on a corner joint. They're very common kinds of welds to make. Things that can make a corner joint easier would be like thickness of the material. As material gets thicker, it gets easier to weld because it can handle more joules before the workpiece falls into pieces. Whereas when you weld thin material, if you do a corner joint, there is a point where you might need to make some sort of backing apparatus where it goes behind the corner and supports the corner, so you can weld and have some of the heat pulled away from the weld pool as you are welding. Although it varies depending on your skill level. You guys are good on joint types? If you have any questions, you can just shout them out or raise your hand, either one. All right, this one I tried to do an animation. All right, so in terms of weld types, so you've got your joint types, which are how pieces of material come together, but your weld type is how the weld looks that are joining the two pieces of material together. Some common weld types are displayed on the screen. You've got a bead, you've got a fillet weld, you've got a groove weld. Plug welds are also pretty common. And the way these are essentially denoted is they're like cross-sectional area of the way they look. So you can see on the screen the bead weld looks like a dome, and that's because it would be on the surface of material, like a butt joint is a bead weld, although it can also be a groove weld if there's a gap. But if you were to cut your piece in half perpendicular to your weld, you would see one of these shapes. Your weld would look like one of those shapes, and that is how you call out your weld type. And depending on the joint, you're basically forced into a certain kind of weld type. So like if you're doing a T-joint or lap joint or corner joint, it is almost always a fillet weld, which is essentially just a triangle. Although that is not a perfect representation of what the weld looks like, because you can imagine that you don't want the weld to just be on the surface of the two plates. When you weld, you want there to be good penetration, and so on these two legs on the bottom of the fillet weld would actually look something more like this. So you'd have, this is what is the simplified drawing, but if you had your two plates here and your fillet weld joining them, there would actually be rounded, most likely into the corner as well. And it would look something more like that if it's an actual good weld. If it is a poor weld, it would be on the surface and actually represent that shape perfectly, but that is not strong, that will break. Because it's essentially just welded to the surface and it will come off like glue, because it'll just rip the top layer of the metal off. Groove welds, they're used oftentimes to fill a gap. And so sometimes when you weld, especially when welding thick material, groove welds, or you'll often choose a groove weld over, let's say like a bead weld, because in thin material, if you wanted to weld it together, you could just weld over the top and you could join it no problem, because you just essentially want to match the thickness of the material you're welding here. So if this is, I don't know, 1/8 of an inch, you would want that to be 1/8 of an inch. And that would be perfectly strong, as long as you get a little bit of penetration in there. A groove weld, very common in like heavy equipment, tractors, is when two pieces of material come together. They're very thick, and so most welding processes can only handle up to a certain thickness. It's somewhere around 1/2 inch, depending on the welder. So let's say you got 3/4 inch plate, and you want to make that weld and you want to make it strong. What you do is you usually bevel the edges like that, and then you would put a weld in the bottom. You would then stack a weld on top of that. You would then stack a weld on top of that, and then on top of that, until you filled that entire gap. And so groove welds are often used on very thick material. It can also be used on thin stuff. It just depends on where you need it. I think bead welds are pretty self-explanatory. They just go on the surface of a plate. You can use them to like fix a crack in some plate, or put two thin plates together. together. A plug weld, they're often used to fill a hole. So if you've got a tank and you need it to be perfectly sealed and it's got a couple holes in it, you can use a plug weld to just fill in that hole. They are also very commonly used when joining two plates together. So you got two plates, and you drill a hole either through one or both of the plates. Let's just say one for now, I guess. And then through this hole, so this is the like cross section, right? You fill down to that plate, that hole full of a weld, and it will hold the two plates together through that hole. I don't think I need to say anything more about that. Oh, so here you can see plug welds and how they're called out essentially. So when you call out a plug weld, you don't call out like you're welding a hole. You call out the cross section. So what I drew here, when you weld through a hole, the cross section will look something like that, which is a square or rectangle. And so you can see that whether it be 3 small holes, it's called out using a rectangle, or even the ovals are also called out using, or slot, I guess, called out using a rectangle. And I'll go over how you denote the welding callouts later in this lecture. Actually, starting now. So welding callouts are super important for engineers because they're how you tell the machinist. Is that a question? No? Okay. Welding callouts are super important for engineers. They're how you tell a machinist or welding shop what you want to do. If you don't know how to do a welding callout by the end of your career, there will be a point if you work as an engineer where you need something welded, most likely. And you will have to learn this, so I'd recommend learning it now. It's super valuable if you're not the welder yourself, because you've got to be able to convey that information on a piece of paper. And this is the convention that AWS came up with, which is like the Welding Society. So, welding callouts. The horizontal line is known as the reference line. So, when you are doing a weld, and you want to call it out, you have an arrow pointing to where you want to weld, and a horizontal line. That horizontal line is known as the reference line. The reason why I'm telling you guys that is because a lot of things reference the reference line. Pretty much all symbols are tied to it, all meaningful ones. The arrow that connects it is simply just pointing to where the weld location is. And if there's a flag coming out of this corner, that denotes that you do not weld that weld in a shop. So in some situations, if something's being constructed in the field, there are times when you need to weld something together in the field. So let's say like house construction. If you're assembling a beam, you can do a lot of the welds in the shop. But if you are assembling the beams on the job site, oftentimes beams will need to be welded together that come to a corner. And that corner isn't exactly known. You can't call that out in a engineering drawing for the building because there's a lot of compounding error when it comes to buildings, and so the location might be slightly off. And so you put a field weld symbol where the two beams would come together, and then you have your welder show up, they assemble everything, and then they do that one weld to finish the project in the field. Okay, yeah. This simple drawing where it says arrow side and the other side, that's important because a lot of the times welds will be taking place on two sides of a plate. Let's say a T-joint, you usually do not weld one side of a plate if it's a T-joint because you'll have a stress concentration at this other side. So if you were to load this side with just a weld there, that stress concentration would propagate a crack through the back of your weld, and it would break off super easily. Welds are strong in, at least T-joint welds are strong in one direction. If you have one weld here, you better only be taking load from that side. And so the arrow side is always specified below the line. So any call out you do below the line is the arrow side. And then for everything you want to do on the other side of the line, you don't need another welding arrow to the other line. You just put all that information on top of the line. That makes sense? So up here is the other side, which would be there, right? And this side is there. Good? So if there's a circle right here, that denotes all around. That means that, like, regardless of what you're welding, so let's say you're welding like a square beam to a plate, right there. If you specify that all around, then it means the weld continues all the way around the whole thing. That makes sense? Pretty simple stuff, not too complicated. Should definitely take good notes on this though. Just a hint. Questions about that? All right, so more welding callouts. The tail of the callout, so where it says tail, this part, is where you can put additional information that is not covered on the reference line. So let's say for your welding project, you only want the person to weld it in TIG. So you would write TIG. And then that locks in the process that you want to use. If you want to use ER70 S2 filler rod, you put that there. If you don't put anything there, it is up to the shop's discretion how they want to weld it, what they think will be the best weld for what the project calls for. So if you want complete control over the process and how it is welded, you need to put information there. You can even put little pictures for how you want your weld to look. So a little tiny engineering drawing for the weld. So let's say you want a fillet weld. That'll work. But you don't want the fillet weld to look like a regular fillet weld. You want it to be a fillet weld that's rounded on the edge. You can call that out at the edge of the weld. And you can do that with just a picture. That make sense? All right, so welding symbols. There's a lot of them. I'll try to cover a good amount. We already talked about plugs. That's a square. We've talked about fillet welds. That's a triangle. That gets denoted on the reference line. So if I were to do it on my drawing, let's say we're welding these two plates together, and we want to do a beveled groove, you would do that right there. And And that would be on which side of the weld? The other side. Right on. And then let's say you want the bevel to be, or the beveled weld to be a certain size. You call that information out always on the left side of the weld. Or, sorry, the left side of the weld symbol. So I didn't give myself a lot of space. So let's say we want a bevel weld, and we want 1/2 inch legs. So that means that it's going to be even on both sides of the bevel weld, 1/2 inch. That makes sense? So if this is the bevel weld, that is 1/2 inch, and that is 1/2 inch. If you want one to be different than the other, let me see if I have. I don't know if I have a picture for that. Oh, no, I do. If you want one to be different than the other, you just add this modifier where it's 1/2 inch by, let's say, 1/4 inch, and then, sorry, I actually drew that backwards. If we're talking about the other side of the weld, the bevel would be here. And you could do 1/2 inch there by 1/4 inch. I didn't write 1/4. 1/4 inch. That makes sense? I think that's pretty much it for this. So oftentimes when you're doing really long welding runs, so let's say you're welding a box and it just has to hold some dry material, and it's really long. So there's the corner, the distance of the box, so that's going into the board. Let's say it's like 8 feet by 8 feet. You don't really need to have a weld that runs that whole length unless you really wanted the box to be watertight, or there was some strength requirement for the box. But let's just say it's a regular box. You can specify a stitch weld or intermediate weld by doing a call out on the opposite side of the bevel. Let's say we're moving to a fillet weld down here. We go up, go that way. We're going to do a fillet weld that's just a 1/2 inch. You would then do, let's say you want it 2 inches long. That denotes, and it's always on the right side, that denotes you just want a 2 inch weld. Even though it's 8 feet, I only want one 2 inch weld right where you called it out. If you want 2 inch welds all the way down, you could go 2 inch by 4 inch. And then that would be center to center, 4 inches apart. Does that make sense? So there'd be a 2 inch gap between these welds. 2 inch gap. You don't specify the gap size, you specify center to center of the weld. I know that's from edge to edge, but that's the same as center to center, if that makes sense. Yeah, that's how you call that out. Any questions so far about welding callouts? No? All right. So groove welds, my little picture that was here before. So let's say you want to do a groove weld that looks like that. You would point to the weld, you go up, go over, and then, because you want it on this side, it'd be below the line, you would then do an X, or sorry, not an X, a V. And let's say you want to specify an angle, do 60 degrees, and you put that here. And then you can call out the legs just like we did before, 1/4 inch. And that tells you that these are going to be 1/4 inch by 60 degrees. If you're welding on 3/4 plate, then that means your bevel only goes down a 1/4 inch. Yeah? And then you can see there, if you want to do bevel on both sides, you do an X, or it's really just another bevel on top, or groove on top. And you can call that out differently, so you can see the asymmetric bevel there, where you do 1/8 inch on top, 60 degrees there. Sorry, the 1/8 inch is the gap. So if you put measurement here, that is, now you've got an 1/8 inch of gap between the two plates as you weld them. Is that good? Same thing if it's just a butt joint. You would just change that to parallel lines, and this wouldn't be beveled, it would just be straight walls with an 1/8 inch gap. Yeah, I think I just talked about that.